Hi, welcome to the Team 4 Heat Exchanger First Evaluation video. My name is Peter Klopp, and I'm joined by my teammates Ben Lehrer and Nina Tedeschi. In this short video, we will be walking you through the design, manufacturing, and initial testing of our heat exchanger, which is designed to achieve the largest amount of heat transfer between two water streams in the smallest bounding box. Here is an external view of our device. On the left side, you can see the 4 inlets and outlets through which hot and cold water are pumped, as well as the primary machine body. On the right side, you can see the sealing cap plate along with 4 elbow fittings and tubing to redirect the flow from the center of the device to the inlet and outlet fittings. Here is an internal view of the device, along with a schematic on the right side showing the basic design. Our heat exchanger is a type of spiral heat exchanger in which heat transfer occurs between 2 parallel counterflowing fluid streams which are wound together in a spiral. On the left side, you can see the machine spiral channels through which hot and cold water flows. In our device, the hot water is first redirected to the center of the spiral and then channeled outward, exchanging heat with the cold water stream in the process. Cold water enters at the outside of the spiral and is channeled to the center, achieving counterflow.
Our heat exchanger was machined at a billet 6061 aluminum, with a 0.1 inch wall thickness being our heat transfer surface between our 2 spiral fluid paths. The overall dimensions of the device are 6 inches by 7 inches by 1 1/8 inches tall. The shell of our device was machined using the Prototrack CNC mill out of this aluminum billet. We first machined the inside with spiral geometry using a small end mill, before moving on and machining the outside. We then tapped the holes by hand. The cover plate was also 6061 aluminum, measuring about a 1/4 inch thick. It was hand cut on the bandsaw and then drilled to allow the sealing bolts to pass through. We also tapped this plate for the 1/4 inch NPT barb fittings. Next, we laser cut and drilled a sealing gasket out of this cork material. Our device connects up to the testing apparatus using the NPT adapter supplied in class. We package these adapters as close together as possible while still ensuring proper clearances to allow the device to be hooked up successfully.
Here you can see our heat exchanger connected to the testing apparatus. Unfortunately, the system in full was not working, so we didn't obtain the temperature measurements. When testing water flow individually through each system, a flow rate of 2 liters per minute and pressure drops of 12.4 and 13 kPa for the hot and cold water systems, respectively, were observed. Examining our device for leaks, we observed no leaks except for a small drip at the bolt hole seen here. This was attributed to the top plate being manufactured by hand and over-drilling the hole. The next iteration of our design, we will apply silicone to this hole to seal this leak, as well as cut the male intermediate adapters seen here to place our adapters flush to the aluminum rather than be offset as they are now for improved volumetric efficiency. From this initial testing, our biggest lesson was how surprisingly effective gaskets and clamping bolts were as an effective seal, initially thinking we'd require more silicone sealing. We also learned that subtractive CNC machining method, which we use, can be quite expensive, time-consuming, and inefficient use of resources. We also ran into issues with adapter interference and needing to have proper clearances around bolts for sealing and wrench clearances, which we'll take into our future designs.